In 6C7, we're going to take a look at how we are going to do practice problems with the valence shell electron pair repulsion theory. And what we'll be doing in these practice problems is we'll be taking how we can get from a formula to the molecular shape, and how we can determine whether the molecule is symmetrical or asymmetrical once we've drawn it using the shape sheet, and how we can determine if the molecule overall is polar or nonpolar, which will enable us to predict many of the physical properties concerning that molecule. All right, here we go. Example problems. Let's take a look at our first example problem. What is the molecular shape of AsH3 arsenic trihydride? What is the molecular shape of arsenic trihydride? Well, we learned that we need to go through the steps to drawing Lewis structures, and the first thing is the electron accounting step. Arsenic is in Roman 5. It has 5 electrons, and we have 1 arsenic in the formula. There are 3 hydrogens in the formula, and hydrogens in Roman 1. It has 1 valence electron. 3 times 1 is 3. 5 and 3, we have 8 total electrons to work with. That's step 1 of how we draw these structures that we learned in Unit 6A. Now we have to pick the central atom. Hydrogen can only make 1 bond. It has 1 electron. It can only make 1 bond. Arsenic has 5 bonds. It needs to make 3 bonds in order to satisfy the octet rule. Arsenic has 5 electrons. It's able to make those 3 bonds that it needs to get 8. So arsenic will be our central atom. In step 2 of our Lewis structure rules, we select the central atom and we surround it with 8. So now we're going to draw the molecule. Arsenic is our central atom, and we're going to surround it with the 8 valence electrons it needs. So now we have the 8 valence electrons around the arsenic, and now we have to attach the 3 hydrogens. We can attach the hydrogens wherever there is a pair of electrons. So now we have our hydrogens attached, and now we're going to count total electrons. I'm supposed to have 8. 2, 4, 6, 8. I have 8. So now I can move to the fourth and final step. I don't have to make any doubles or triple bonds or anything like that. I don't have electrons that I need to erase. All I need to do for the fourth and final step is replace each shared pair with a line. And now we have arsenic trihydride. So now from our Lewis structure, we have arsenic trihydride. From our Lewis structure, we can determine the shape of this molecule by counting. We want to count the total things surrounding the arsenic, which is our central atom. There are 3 bonded atoms and 1 lone pair. That lone pair counts as 1 thing. Each atom counts as 1 thing. That's 4 total things. B are the hydrogens. That's bonded atoms, not number of bonds. Our E is 1. That's electron pairs, not electrons. So our total is B plus E, which is 4. Our B is 3 bonded atoms. Our lone pairs are E, that's 1. So when we use our shape sheet, we're going to be looking in the 4 first column. And then we're going to find the 3-1 combination. So our total things were 4. We're going to be looking in the 3-1 combination. Our B is 3, our E is 1. There we go. We've got that. That's very simple. The shape formula, all we do is put the 3 as a subscript next to the B. E is our lone pairs of electrons. We put that next to the E as a subscript, and E sub 1 is the same as an E. What's the name of this shape? Trigonal, pyramidal. What are the angles between the atoms? 107. A tetrahedron has 109.5. But that lone pair of electrons will push that angle from a 109.5 closer, making it a 107, because that bonded or that unbonded pair, that lone pair, is able to repel those bonded pairs down more tightly. That's an asymmetrical shape. That lone pair bends it so that the atoms are not evenly distributed. So from the shape sheet, we can say that it's an AB3E1. The shape is trigonal or trigonal pyramidal. The bond angle is 107. I have these 3 hydrogens being pushed downward. I have the lone pair sitting on top. That's not evenly distributed. We would have to have a hydrogen up here for them to be evenly distributed 3-dimensionally. Again, this is a 2-dimensional drawing. So the shape is asymmetrical. Before we can determine whether the molecule is polar or nonpolar, we have to remember what you need for it to be considered polar. For it to be polar, as it's written right here on the shape sheet, it's polar if and only if. IFF stands for if and only if it's asymmetrical, which it is, and if the bonds are polar covalent. So we'll need to use an electronegativity table to look up the electronegativities of arsenic and hydrogen. On the electronegativity chart, we see arsenic is 2O, hydrogen's 2,1. The difference there is 0.1. Looking right here on the chart, if it's 0 to 0.3, in this class we call it nonpolar. Some classes go to 0 to 0.4. Some all go all the way up to 0 to 0.5 and call it nonpolar. So the bonds here are nonpolar, which means that the molecule itself doesn't have polar bonds. So there are no little dipoles. If there were little dipoles, they wouldn't cancel out because it's asymmetrically shaped. But there are no little poles because it is not polar covalent. So we haven't met the qualifications for it to be considered a polar molecule. Therefore, the molecule is nonpolar, even though it's asymmetrical. So on our sheet right here, we would write down that it is, as we can see the star here, it's nonpolar. There are not partial negatives and partial positives. So we would expect ASH3 to be a gas that wouldn't stick. Yes, it's asymmetrically shaped, but there's not a polar bond to establish partial positives and partial negatives. The next molecule we're going to be drawing is silicone tetrachloride. Silicone tetrachloride has 1 silicone and 4 chlorines. The chlorines have 7 valence electrons. It's in Roman 7. 4 times 7 is 28. And silicone's in Roman 4, so it has 4 valence electrons. 1 times 4 is 4. Our total electrons that we're working with is 32. Who will be in the middle? Well, chlorine only needs 1 bond. Silicone needs 4 bonds. It has 4 electrons. It needs 4 bonds to get 8. So silicon will be our middle atom. So we're working with 32 electrons here. Silicone will be in the middle. And now, according to the Lewis rules, I will surround silicone with 8. We now have silicone surrounded with 8, and our Lewis rules now say to attach the chlorines wherever we have a pair of electrons. So I have to attach the 4 chlorines. I now have the 4 chlorines attached. I now need to surround them with 8. Hopefully we have the chlorines now surrounded with 8. And Lewis tells us in our next, as part of this step, we now need to count our total electrons to see if we have the right number. We're supposed to have 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. There's 8 around each of the chlorines, and there's the shared pairs. So at this time, we now replace the fourth and final step. We'll replace the shared pairs with lines, indicating a bond has formed. So we have our silicon tetrachloride molecule, and now we're ready to determine its 3-dimensional shape and determine is it polar or not. We know it's already symmetrical because there's no lone pairs on that silicone to push the chlorine atoms into a distorted asymmetrical shape. One thing that is important to point out, symmetry means that you have the same atoms surrounding it. So silicone here has 4 chlorines, but if one of these atoms weren't a chlorine, or 2 or 3 were different atoms surrounding it, then it would be asymmetrical. Symmetrical, you have to have the same atoms spread evenly 3-dimensionally in the space surrounding the silicone. But we do have the 4 chlorines, so we know this is symmetrical, but we will prove that and verify that using our VSEPR shape sheet. All right, we can now begin counting, and the first thing we count are the total things. As we can see right here, we're going to count the total things. The bonded atoms, not the bonds, the bonded atoms around the central atom, and only the lone pairs on the central atom. These lone pairs on the chlorines do not impact the shape of the molecule. So we have 4 chlorine atoms, we have no lone pairs. So our total is 4. With our total 4, we know that the 4 things are made up of all bonded atoms. So our B is 4. If we have 4 total things and all of them are bonded atoms, that means our central atom doesn't have any lone pairs, and we see that there are no lone pairs on the silicon. Our shape formula then, we take this 4 and insert it as a subscript by the B. The 0 we can insert as a subscript by the E, or we don't even have to put it on there. E0, we don't even need the E. So we'll substitute those numbers in. And now we can go to the shape sheet. Our shape formula is AB4E0. We're looking in the 4 leftmost column, and then we're going to proceed to find the 4, 0 on our shape sheet. So our leftmost column, we're looking for the 4. Our B is 4, our E is 0. Our shape formula is in fact AB40. That means our shape's name, the name of our shape is tetrahedral. So on our shape sheet, under shape name, we write tetrahedral. We now look to the next column over, and we'll see our bond angles are 109.5. The bond angles of the tetrahedron, 109.5. Bond angle 109.5. We already know that this shape is symmetrical because there are no lone pairs, but let's see if the shape sheet agrees with us. Here we are. Yep, it is symmetrical, which means the molecule is nonpolar. There cannot be a net dipole. In order for the molecule to be polar, it has to be both asymmetrically shaped. For it to be polar, there are two conditions. If and only if it's asymmetrically shaped and the atoms are not sharing equally, giving rise to polar covalent bonds, which creates the little mini dipoles. So, tetrahedron is symmetrically shaped. It is a nonpolar molecule. There's no net dipoles. There's no partial charges. So if it's symmetrical, you can pretty much go straight down to the nonpolar column and put the answer there. These little stars are the ones I'm picking. So I'm picking it as nonpolar. It's symmetrical. However, they did ask us to calculate, is the bond trying to be polar or not? So if they are asking for the type of bonds, we need to figure it out. And we need an electronegativity table to determine the electronegativity differences. Looking on the electronegativity table, we'll see chlorine's 3O. The silicon is 1.8, so we can go ahead and put those on our chart, 3O and 1.8. 3O minus 1.8 is 1.2. That is polar. So the bonds are trying to be polar. The chlorines are trying to pull the electrons to them. The problem is, since it's symmetrically shaped, they are pulling against each other, equal and opposite. So all the little dipoles that are trying to form end up canceling out. Our molecule then, that's what makes it nonpolar. When it's symmetrical, whether there's polar bonds or not, the molecule is going to be nonpolar. There are no partial positives or partial negatives, so there won't be an intermolecular force called a dipole. We will learn about other intermolecular forces called London dispersion forces, which can enable molecules to stick together, but the sticking together is not the result of dipoles. On our next video, we'll take a look at the carbonate ion. It's CO3 2-, and we'll remind you of how to deal with charges on molecules.